Welcome to Root Research, where we decode science into decisions you can actually use. Today we're talking about a wild idea. You can teach electricity to prefer one direction just by twisting a crystal into a tiny helix. Shown by Max T. Birch and Yoshinori Tokura with collaborators. What if your electronics could get smarter without changing the material at all? Picture your phone charger. Inside there are diodes, little one-way doors for electricity. They're everywhere. Chargers, LEDs, radios, basically the plumbing of modern tech. Now here's the hook. Birch and the team showed something that sounds like sci-fi but is very real. Take one crystal, carve it into a nanoscale spiral, and it starts behaving like a diode. And not a boring diode, a switchable one. Why should you care? Because we're hitting limits. We want devices that are smaller, faster, cooler, and more energy efficient. But traditional chip design mostly plays the same game. Pick a material, stack flat layers, hope physics cooperates. This research says, what if shape becomes a new knob we can turn? Like material is, like voltage is, like temperature is? So what did they actually build, and why is it such a flex? They worked with a special quantum material called CO 3SN2S2, a magnetic whale semi-metal. Don't worry, we'll translate that in a second. Then they used a tool called a focused ion beam. Imagine a nanoscalpel that can sculpt a crystal by blasting away atoms with insane precision. They didn't just cut a flat wire, they carved three-dimensional helices, tiny spiral staircases, made out of one single crystal. This matters because a lot of nanofabrication methods either can't do true 3D shapes well, or they force you to use only certain materials, or they damage the material so the cool physics disappears. Their approach is basically, start with a high-quality single crystal and sculpt the device directly out of it. Okay, but how does twisting change how electricity flows? Here's the everyday picture. Think of walking through a hallway. If the hallway is straight and smooth, it doesn't really matter which direction you walk. Now imagine the hallway is a spiral tunnel with weird curves and corners. Suddenly, the path feels different depending on direction. You bump into walls differently, you take turns differently, you slow down differently. Electrons can behave like that too. In their helical devices, the team saw non-reciprocal transport, meaning current flows easier one way than the other. And the kicker is why it happens. The helix has handedness, left-hand spiral versus right-hand spiral. That breaks a symmetry called inversion symmetry. Basically the idea that forward and backward look the same. The material is magnetic, which breaks another symmetry, time reversal. Roughly, physics behaves differently when you reverse the direction of time/motion. When you break both of those, electricity can start acting like it has a preferred direction. This is why the team didn't just twist any crystal. They chose one where magnetism and electron motion are already interesting, then added geometry as the extra ingredient. Switchable diode sounds cool. What does switchable mean here? This part is genuinely fun. They showed the diode direction can be reversed in two ways. 1. Flip the magnetization, think magnetic north/south orientation inside the device. 2. Flip the helix handedness, left-hand spiral versus right-hand spiral. So it's not just a one-time, we built a diode. It's more like, we built a diode whose direction you can control. And there's an even spicier reverse gear result. They also observe the inverse effect. Strong electrical pulses could switch the magnetization. In plain language, the current doesn't just obey the magnetic state, it can also change it. Where does the diode effect come from? Magic quantum stuff or simple physics? Birch and colleagues didn't stop at "it works." They tested helices of different sizes and temperatures, then connected the behavior to something you can visualize: electrons scattering unevenly along curved walls. Here's the simple mental model. In some materials, electrons don't crawl like tired ants. They can move more like a fast crowd, sometimes almost ballistically, meaning they travel a long distance before bumping into something. If the mean free path, how far an electron goes before a collision, becomes comparable to the curvature size of the helix, then the walls and curves start to matter a lot. In a helix, that bumping pattern isn't symmetric, so going forward isn't the same as going backward, and you get a built-in directional preference. The team even argues the effect is much larger than what a simple classical self-field explanation would predict, which supports the idea that geometry plus high-mobility transport is doing real work here. So what's the big idea Tokura's group is pushing? Tokura's quote in the write-up basically lands on this theme. Treat geometry like a first-class design principle, right next to which material did you pick? In the classic electronics mindset, shape is mostly boring. Make it small, make it connect, don't break it. In this mindset, shape becomes active. It's like a knob that can break symmetries and unlock new behaviors, especially when you combine it with quantum materials that already have exotic electronic states. What real-world problem could this help with? Like, something you'd actually recognize. Let's pick one likely direction: future memory and logic that wastes less energy. Here's a hypothetical situation. It's a few years from now. You've got a smartwatch that tracks sleep, heart rate, stress all day, every day. The bottleneck isn't can it measure stuff, it's battery. The device is constantly moving tiny signals around, and every unnecessary loss becomes heat, and every heat becomes wasted energy. Now imagine the circuitry includes tiny switchable diodes that can route current differently depending on their magnetic state. Kind of like having a smart one-way street system for electrons. When the watch is idle, the pathways default into an energy-saving traffic pattern. When it needs to process data quickly, it flips the pattern. The point isn't that your next smartwatch will literally have helical Weyl semi-metal parts. The point is, they demonstrated a new lever, geometry-driven reversible directionality, that engineers can try to translate into practical device architectures. And because they sculpt directly from single crystals, in principle this becomes a platform. Try other crystals, other curvatures, other quantum states, and see what new functions fall out. If we zoom out, what's the main takeaway you should remember tomorrow? If you remember one thing, make it this. Electricity doesn't only depend on what a thing is made of, it can depend on the shape you carve it into. Birch and collaborators showed that a nanoscale helix carved from CO3SN2S2 behaves like a switchable diode, where the direction of easier current flow can be reversed by changing the magnetization or the helix handedness, and electrical pulses can even switch the magnetization back. That's a pretty bold message for the future of electronics. Geometry can be engineered as a source of symmetry breaking, not just an afterthought. And that could reshape how we design memory, logic, and sensing devices when flat design starts to feel like a dead end. Big thanks to Max T. Birch, Yoshinori Tokura, and the whole team for pushing materials physics into this sculpture meets electronics territory. If you like what we do at Root Research, subscribe, and drop a comment with one device you wish could be smaller, faster, or last longer on battery.